Swayam Prabha. Digital India. Educated India.
Hello everyone, my name is Bonal Lautiman from Department of Chemical Engineering, Chulalongkorn University, Thailand. Today I would like to present my work in the topic of battery aging monitoring of single battery using linear parameter varying model construct from electrochemical impedance spectroscopy. For the outline, I will provide a brief introduction about the background of single battery and objective of this work. The methodology of this work includes the description of battery I use in this work and also the data collected from the battery. Then I will talk about how the battery was modeled using EIS and the LPV modeling. And the next section is the result, including the correlation of the model and the validation, and close the presentation with conclusion. Firstly, we start with the introduction. Nowadays, energy storage system is the center of research spotlight. Battery is one of the most general and most commonly used energy storage system. Among many types of the battery, metal air battery is very interesting due to its specific energy as shown in this figure. The specific energy of metal air battery is higher than the other commercial battery. That is its advantage. And for the metal air battery, zinc air battery is quite the most interesting one as shown in the table on the right. Specific energy of zinc air battery has the smallest gap between theoretical and practical values. And it uses alkali electrolyte, which is very common electrolyte and easy to operate. The key advantages are that zinc metal is very abundant. The battery is safe and not explode. So it is friendly to environment. And next is zinc can be regenerated by various procedures, especially electrochemical recharge. Therefore, the zinc air battery is the rechargeable battery. Also, the performance of zinc air battery is progressed every year. And now the energy density of zinc air battery was able to reach up to 800 watt-hour per kilograms. Zinc air battery generally consists of two electrodes, zinc electrode and air electrode. At zinc electrode, zinc react with hydroxide ion and form zincate ion and electrons. Zinc ion further convert to zinc oxide when zincate ion is saturated in the electrolytes. At air electrode, oxygen react with water and receive electron, then produce the hydroxide ion. The overall reaction is shown as zinc react with oxygen and form zinc oxide. So the theoretical cell standard cell potential is the 1.65 volt. And for charging, the reaction reversed. State of battery are significant for the operation of the battery management system, as the true state have to be delivered. The state that studied here in this work is the state of health. State of health relates to the aging phenomenon of the battery when the battery has been used, it prevents degrades. Previously, state of health had various definitions, has various versions that has been proposed. For example, capacity fading state of health is the ratio of actual maximum capacity and the rate maximum capacity of the battery. Or the internal resistance dependent state of health is related to the rate resistance and actual resistance of the battery. So the objective of this work aims to develop the linear parameter varying model or LPV model for single battery with the state of health as the scheduling parameter and use it to analyze the feasibility of battery aging monitoring. Next part is the methodology. As regards the battery that we use, the laboratory-made single battery was fabricated as shown in the diagram. This cell configuration has two electrodes, including air electrode and zinc electrode. the support structure made of polyacrylic acid, PMMA, and the cell is filled with electrolyte which is 7 molar potassium hydroxide solution with 4% of zinc oxide. The anode active material is zinc electroplate on current collector, which is copper plate. Cathode active material is oxygen in the air, and the oxygen reaction occur at the cathode current collector, which is nickel foam coated with catalyst and gas division layer. To obtain the battery data, the fabricated battery was operated using procedure shown in this slide. At the first, the battery was charged with current of 20 milliamps for 5 minutes. Then it was discharged at 20 milliamp current for 5 minutes and test EAS 3 times. After that, the battery was cycling with the same charge and discharge condition for 10 cycles. Then we repeat the process of testing EAS again. For the ES or electrochemical impedance spectroscopy, either the test that the battery is injected with the sine wave signal input, and in this case, it is injected by the sine wave of the voltage, and then the output signal, which is the current, was observed. The voltage and current respond in time domain at various frequency, so we can transform it into the frequency domain data, and then the impedance data can be calculated from at each frequency as shown in the Bode plot. The popular useful plot for EAS are Bode plot and Nyquist plot, which is the plot of imaginary impedance versus real impedance. This plot are used to fit with the model, which is the equivalent circuit model. So the model that we use is the equivalent circuit model is in the form of second order RC circuit model, which is shown in this slide. The model consists of R or resistor, C or capacitor. However, the electrochemical reaction inside battery, the impedance behavior of the capacitor is close to the constant phase element, which is the non-ideal capacitor. So we will use the CPE or Q element to calculate the impedance for the battery. And this slide shows the equivalent circuit model with the impedance equation. R0 is represent the ohmic resistance. CP is the capacitance of the electrochemical double layer, and RC is the charge transfer resistance, and the equation is shown below. And as I mentioned before, we replace the capacitor with the constant phase element or Q, and the equation changed to this equation. And this model with the constant phase element was used to fit the data with the result of EIS. However, the developed model will be validated with the direct current data, so we have to change the CPE back to the capacitor by this equation when we validate the model. And the circuit used to validate is look like this. The cell voltage can be calculated from open circuit voltage and the potential across the circuit, which is VR0, VRC1, and VRC2. The DC voltage of each element can be calculated by the following equation. VR0 is calculated by Ohm's law. VRC can be calculated by the discrete time space equation as shown in the table. And also the open circuit voltage, VOC, is calculated from the relation is the function of SOC. To construct LPV model from the equivalent circuit model, the equivalent circuit model parameters are set to be varying parameter, and the state of health is selected as the scaling parameter. For this work, state of health for single battery was defined as the ratio of actual energy efficiency to the maximum energy efficiency. Energy efficiency is the ratio of discharge to charge energy. The maximum energy efficiency is usually used the first efficiency of the first cycle. To summarize the procedure, the battery data was obtained by cycling tests and has different state of health in each cycle. EAS will conduct to get the parameter and then create the LPV from this parameter, and then the model will be validated. Next part is the result. For the ES test as shown in the slide, when the cycling test is going on, state of health decrease and the impedance or increase instead. The equivalent circuit model parameter extract from the ES test was fit into the correlation as shown in this slide. The function used to fit the correlation were the polynomial function and the exponential function. For validation, at first, it was validated with the same data that used to create the model. The plot shown in the slide is the applied current profile, and we have separate discharge and charge profile separated. Start it with discharge. Cycle 50 and 100. State of health can be calculated from the data and input can be used as input to the model. The prediction in this result has some error shown in the response. However, the state of health can be adjusted to improve the model accuracy. As shown in the slide, the new state of health values provide higher model accuracy. And next one is the result of the charge response. Same as before, the calculated state of health were input to the model, and there is an error occur at the chart voltage plane. And same as this chart, the state of health value were adjusted to provide more precise prediction. The error occur might come from the correlation of fitting, or it might come from the fact that the SOH is not defined correctly. Next validation test is the data from the different battery. This data come from the response of a charge-discharge cycle, so it will include charge and discharge in one plot. The plot shown in this slide is the applied current profile. At cycle 100, prediction with calculated state of health of 0.75 shows some error. So while adjust state of health to 0.52 was able to reduce the error. Another example is from cycle 200. The result is same as cycle 100. State of health have to be adjusted lower to get better result. This result emphasizes that there might be some incorrectness in the definition of state of health. However, the LPV model was able to sense the changing in the battery aging via the proposed state of health. By defining state of health properly, the model might be able to predict the data more correctly. Conclusion. Battery aging of single battery was investigated by using EAS and LPV modeling. State of health for single battery was defined. The equivalent circuit model parameter obtained from EAS were used to develop LPV model with state of health as scheduling parameter, and adjusting state of health can be improved the model prediction performance. Thank you.
Thank you for the wonderful talk, and let's thank the speaker first. And yeah, questions?
Hi, the good talk. Some few questions I have. Like you have used EIS to characterize the battery. So could you please talk about what the frequency range you use?
For the frequency, I use the start from the high frequency, which is 200K, to the lowest frequency I use is the 0.1. Yes, 0.1 hertz. Yeah. 100 millihertz. Yeah. So the rest time between cycle. So I rest for charge at the in this line. I charge for 20 minutes, 20 milliamps, and rest for 5 minutes. No, sorry. I charge for 20 milliamps for 5 minutes and discharge for 5 minutes and then rest for 5 minutes. And then I test EIS. So, but when I cycling for another 10 cycle, I don't have the rest period in the cycling. Actually, we can use various type of model to fit the result of the test. But because I would like to convert the ECM into the LPV model, and the reason that I use second order is because it represents the structure of the battery clearly. Like we have one loop of RC, which is represent one electrode, and the second loop RC also represent the electrode. So the first loop that provide the faster response will be represent the zinc electrode, which is usually faster than the air electrode. So the second RC loop will represent the air electrode.
Okay. Maybe you can try with the third order or something, because I saw some graphs had some error in the SOH value, some predictions. Maybe because the same data can be fitted to the third order, or there is no universality to it. So maybe that might help in your predictions for SOH, I guess. There are some errors in cycling at a higher cycles, like you showed in the results. Maybe that helped.
Yes, sir. Yeah, maybe we can try add another RC loop, and it will reduce the error. And also, actually, for the equivalent circuit model in that the researcher usually try with EIS, they have some other elements like Robert element that represent something about the diffusion or mass transfer. Yeah, but the use third order could maybe can be reduce the error of the test. Thank you.
Thank you once again. With that, this session is closed, and we will have the next session starting at 2 o'clock, and lunch is served in the nearby hall. So we'll start the session at 2 o'clock. It will be again on monitoring and diagnosis. Thank you.